Laura Marchal-Crespo. Laura is Associate Professor at Department of Cognitive Robotics, Faculty 3ME, Mechanical, Maritime, and Materials Engineering at Delft University of Technology in the Netherlands. Her research focuses on the general areas of human-machine interaction and biological learning, and in particular, the use of robotic devices and immersive virtual reality for the assessment and rehabilitation of patients with acquired brain injuries. Okay, Laura, the floor is yours.
Okay, thank you. 1 second, I need to put things fine in my screen. So actually I don't see you at this moment. But you see my presentation, right? So that's the important thing.
Yes.
Good.
Yep.
Thanks, Heike. Okay, well, thank you very much for the introduction and for inviting me to the organizers. So today I would like to talk about our journey towards finding the role of haptic interaction with robots for promoting motor learning, and use this knowledge about how people learn with robots to be exploited in rehabilitation, for example, of stroke patients. So as said, I'm an associate professor at the TU Delft. I also work very closely with Erasmus MC in Rotterdam, and I am also part of the University Hospital Bern in Switzerland. And I have a very interdisciplinary group that actually is international because I have 2 labs, and we work together in order to enhance the recovery of stroke patients. So what we do in the lab is we develop new robotic devices. We also use commercial ones. We combine robots with virtual reality and with brain imaging. But one of the things that I have been doing since the beginning of my research journey is to look into how to make these robots move in the way that we are maximizing the learning. It could be the learning of playing tennis, for example, relearning to walk, and so on. So how to have controllers that are moving the robots in order to maximize this learning. So all my journey started more than 15 years ago in the University of California at Irvine, but I started working with children with cerebral palsy. And the project in there, that was my PhD, ultimate goal was to create a smart wheelchair that was able to teach children how to drive a power wheelchair. So what we did was to have a commercial wheelchair at a very low cost camera and a robotic joystick. And this robotic joystick, what was doing was to push the hand of the children in the correct way in order to steer the wheelchair. And the task to be done was to follow a black line on the floor. So the camera was seeing the line, and then the robotic joystick was turning to the right and to the left in order to teach the child how to learn. And when we were looking into how the therapists were providing this kind of teaching, we realized that actually the therapists are not always providing 100% assistance, but they are only providing the assistance as needed in order to be able to fulfill the task in a safe way. So we went for a kind of haptic strategy that was providing assistance to steer the power wheelchair in a way that the amount of assistance was reduced as the children were learning, what is called assist as needed. That actually it's nowadays still quite in use. So we ran an experiment with healthy children and 1 child with cerebral palsy. And we have 22 children that were split into different groups, the ones who learned with assistance from the robotic joystick and the ones that were steering when the joystick was transparent, so was not doing anything. And so we asked them to go through this course on the ground. And the first time they went through, it was without assistance. And then the second time that they were going through, already the assistance was on. Here in red, you can see the error, that it's the distance between the wheelchair to the line of the children who were training without the assistance. And in blue, you can see the children that, by the way, were healthy children who were training with assistance. So you can see that in the moment that the system was on, the errors were reduced in the group of assisted children. The error was increasing slightly because the assistance is is reduced. And in the last 2 labs, there was no assistance. And what we found is that the children that was learning with the assistance from the robotic joystick in the wheelchair significantly learn better than the children who learn without any assistance. We also ran a proof of concept with a child with palsy here, Alexa. And we saw that at the beginning, she was actually not able to steer the wheelchair, but in the moment that the assistance was on, the error reduced to the same level as the healthy children with assistance. And then at the end of the training, her error was similar to the children, with the healthy children without assistance. So somehow we were happy, because then that means that actually having assistance from robotic devices seems to help people to learn to perform tasks in a safe way and also in a motivating way. But it's not always the case. If we look into the literature, we see that many motor learning experiments actually conclude that this type of haptic guidance hampers the learning, because what it's doing is just trying to make the actual position of the person with forces to the desired one. And by doing this, we are reducing the possibilities of making errors. And we humans learn mostly by making mistakes. So some other researchers stated that actually, instead of reducing the errors with haptic guidance, it will be better to actually amplify those errors. So applying forces that are pushing the position, the actual position of the person away from the desired one. By doing so, we may increase the motor learning, because the bigger error, the bigger is the reaction to that error, and the learning may be faster. And also increases effort, because you are not guided, so you really need to be actively doing the task and even fighting against this assistance. More recently, it also has been said that it's not that much about the size of the error, but the variability of this error. So how variable are the movements are a predictor of how fast we learn afterwards. And if we look into the literature, so there are some conflicting conclusions, because actually, what is the best training strategy? What is the best way of moving the robot? Should we provide haptic guidance, or should we do error amplification? Should we find a way of amplify or maximizing this variability? So in order to answer this question, some years ago, when I was a postdoc at ETH together with Heike, we ran this experiment with Marcos. Marcos is a MRI-compatible exoskeletons that it's overactuated. It has one cylinder that can move the knee of the person up and down, and a second cylinder that can provide forces that resemble the ground reaction forces. In this experiment, the second cylinder is not in use. So we wanted to run an experiment where we were comparing in healthy people the effect of different control strategies on learning of a stepping-like task inside of the MRI, because we were interested in having a look into which brain areas were activated during the learning. So we ran an experiment that was quite of a tricky task, and it consisted in trying to synchronize your legs in a way that you were following a Lisa Joyce figure on the screen. So when people were moving up and down the left leg, you see hopefully a green dot that is moving up and down. When moving up and down the right leg, the green dot is moving to the right and to the left. And then you need to learn how to synchronize the amplitude of your knees and the time in between the knees in order to be able to follow a white dot that is moving on top of the ellipsoid. So we split, well, we developed different controllers in order to be tested. The first one and the obvious one is to provide a PD controller, and in parallel with an interactive learning feed-forward controller in order to reduce as much as possible the error, because we were using a cylinder, so with high friction and so on. But actually, in a preliminary study, we realized early enough that using this robotic assistance was not a good idea. So we move on in order to make the robot to be as transparent as possible, so the people could train to do the task without any assistance or resistance from the robot, so what we call the no guidance technique. Then we also developed an error amplification strategy that what was doing was making the robot to amplify the tracking error, so the distance between the green dot and the white dot, in a way that you were providing higher forces to prevent you to be on the correct spot, as bigger was the error. So similar as a P controller, but with a negative value here. So this kind of error amplification results in big errors, as you can see. So in the blue line, the blue signal here is the desired movement, and the green dash one is the actual one. And also, this is the standard deviation in blue, and the mean and the mean of what was performed was the dashed line. So it results in relative big errors and also a bit of variability into the movement. But we were also interested in only augmenting the variability of the movement and not much about augmenting the error per se. So we also create this controller that is providing noise force disturbance. So those were random forces that people didn't know the value and didn't know when they were gonna happen. And the result of these forces is that you can see these sharp changes into the actual movement of the knee. But if we look into the mean and the standard deviation, we see that the mean that is in dash, it's more or less the same as the desired one. So no big errors are created while the variability still is high. So then we can see which one is better, the one that is amplifying the errors and the standard deviation, or only the one that is augmented the standard deviation. So we ran an experiment with healthy people. We didn't use the robotic assistance one because we realized it was not very useful. And then we asked them to do this task inside of the scanner. And there were several trials. So the first trial was baseline. So there was everything was transparent. So they could try by themselves. The same in the last one. While during training, we have in error amplification is the lighter line here. So you can see errors augment. So the controller works. Random noise in green, and the no guidance in blue. And if we look at it, actually, it seems like everybody learned independently of the training strategy that we were providing. But if we look more into detail of who are the people who benefited most from the different controllers, we can see some differences that are important in here. So we split the participants into two groups. The ones that were in baseline were very, very bad doing the task, and the ones that were quite good. So the skill and the novices. And then we look into the error reduction between baseline and retention with the different controllers. And what we found is that actually novices, the ones that were really bad during the baseline, benefited more from not having guidance, while the people who were initially more skilled benefited more from the error amplification, while everybody seemed to benefit from the random disturbing forces that was enhancing the variability. Thus, what it's saying is that actually it does not seem to be a clear haptic strategy that it's helping learning to everybody. So it really depends on the skill level. Importantly, as we were also looking into the brain areas activated during training, we saw a higher involvement of the emotion and reward areas during the no guidance compared to the error amplification. It seems like having these large errors, although it was good for the skilled subjects, it was resulting in low activation of the reward system. And this is quite dangerous because what we want to do is to keep people motivated because we want people to keep moving and moving. So it seems like, there is not a clear response to what is the best training strategy, and it depends on the skill, but it may also depend on other things. So here you have two videos. On the left, you have one of my students that is trained to perform a task that is moving up and down the arming, our 6-degree freedom exoskeleton, trying to put the center of this ring as close as possible to the green line. On the right, it's very similar movement. The range of motion is the same, but this one is actually a discrete task. It's a fast movement that you are doing from one moment to the other. You don't have to be constantly minimizing the error in the tracking task. And we cannot expect that one training strategy that is helping to perform one task is always going to help to perform the other task. Because even if it's exactly the same movement, you are using different feedback and feed-forward commands from your brain. So in order to answer the question of what is the best haptic strategy, we started a titanic exercise of trying to look into the potential roles of the skill level and the task to be performed on the effectiveness of the different haptic guidance. So this is just a very summary of what initial steps that we did in our own research group, but you can find the review that was last year published in Transactions on Haptics. And basically the conclusion is that the optimal training strategy depends on the skill of the person, but also depends on the task to be performed. But while doing this table and while looking into all the literature, we realized that actually most of the tasks that we were reviewing were very artificial, and they were all based on lab, right? So yes, you know, everything that I show you till now, it's quite artificial. Well, if we look into the environment and how we interact with the environment, we realize that when we perform most of our activities of daily living, those incorporate the interaction with elements who also have a dynamics. And we use our arms and we use our hands in order to be able to successfully perform these tasks. And that relies on all the somatic feedback that are coming from our fingers and from our muscles, that it's feedback to your brain. And then we thought, okay, so we want to learn to perform activities of daily living. We want to improve motor learning, and we want this motor learning to be useful for activities of daily living. Then what we should be adding this interaction with elements during the training. And this is where we start working on to looking into the effect of having the somatic feedback in form of haptic rendering, so the haptic rendering of interaction with virtual elements during the motor learning experiments. So to enable the somatic feedback, we first need to be able to provide this haptic rendering, and we have very bulky, you know, low friction, high inertia exoskeletons in the lab. So we need first to maximize the exoskeleton transparency in order to provide this haptic rendering. This is not an easy task, but we achieve it by adding some force sensors between the contact point of the person and the robotic device, and using disturbance observers in order to maximize the transparency. Once the exoskeleton was ready to perform the experiment, we set up an experiment that consisted in learning to invert a pendulum and keep it inverted. And the dynamics of the pendulum were in place, and we were providing the haptic rendering of these dynamics into the end effector of the exoskeleton. So the people who were performing the task, they could feel the forces, you know, the weight, the centrifugal forces, everything on the end effector of the robot. And then we wanted to see if there is interference between the assistance and the perception of the haptic rendering. So we asked people also to train with a level of assistance. And in this case, we went for the one that is actually the most used into the clinics, that is the human arm weight support, just to alleviate the weight of the arm. So we ran an experiment with 40 healthy participants, and we split them in 4 different groups. The first one was training with without assistance from the robot, but with the haptic rendering in the end effector, so haptic rendering of the dynamics of the pendulum. Then 10 train with the supported haptics with assistance and also with haptics. 10 train with only the visual information from the game, and then 10 train with the supported visual. That is basically what people are doing during the rehabilitation, right? So they have the assistance and they only have visual information from the game, so no haptics in there. We also were very interested in to see if by learning to perform this task with a specific pendulum, we could transfer this learning into performing a similar task, that is inverting a pendulum with different dynamics. And in this case, a pendulum with a shorter length. This is the transfer task. And those are the findings. I hope you can see my mouse here. So on the right of the graph, you can see when the assistance was on, so weight support on, and on the right, weight support off. And then in blue, you can see the haptic rendering off, and in orange, the haptic rendering on. And what we saw is that, of course, when we have the assistance on, so the weight support on the right, the amount of torque that was required to perform the task was smaller than without body weight support. And also that when we were having the haptic rendering of the pendulum, we also increased the amount of torque that the people were putting into the game. So it was increasing the effort. We also saw that people were performing more variable movements when the assistance was on. That it makes sense because it's facilitating the performance of the experiment. But more importantly, it also was enhanced this variability when the haptic rendering was on. So having the haptic rendering enhanced variability that now we know that this variability is good for motor learning. But what about the learning? So we saw that when we were adding the haptic rendering on here in orange, the increase of the score was significantly bigger than without haptic rendering. So actually having haptic rendering was enhancing motor learning. On the other side, having assistance on top of the haptic rendering, it was reducing the increase of the score. But remember that this is healthy people. So we cannot say the same with a stroke. And about the transfer, we also saw that having this haptic rendering in one type of pendulum also helped to transfer this knowledge into performing successfully the task with the pendulum with a shorter length, with different dynamics. So it was good for transfer of learning, while without haptic rendering, it was much smaller, significantly smaller. But again, we saw interference with the assistance in here. So all indicates that if you want to train a task that involves the interaction with dynamic elements, then you have to add this information during the training through the haptic rendering. So most probably you may be thinking when I show you the video of the people jumping and playing the guitar, everything was performed with the fingers and we interact with the environment using our fingers. But what I ran was an experiment with an exoskeleton. You are holding a stick. And I agree. And that's why we are making an effort into developing a new hand model that is able to provide this nice haptic rendering. We do this in a way that is minimally actuated with only one motor that it's able to provide also assistance to open and close the hand from full extension to flow flexion, and that it's very transparent to be able to provide this haptic rendering. So here I want to show you a video that I hope that it shows well of our invention. This is Sprite, and you will see that the first thing that we do in this video is to change this handle in here. And this handle here, what it's doing is to optimally locate the metacarpal joint of your hand in order to be able to physiologically follow your hand. And for different hand sizes, we have different handles. So now we change the handle to the one that is optimal for the person. Now it's very easy to put the person inside because you only have to slide your hand. And now the metacarpal joint is optimally located. And this is very beneficial because this movement, because it's very easy to also mount people that are very spastic into the device. You only have to slide it. There is no need of spending 30 minutes there. And with only one motor, we are able to support the full extension of the hand and the full flexion. So we combine our hand model that we can mount into exoskeletons, or we also can mount into end effector robotics, such as, for example, this one here is mounted on a lambda from first dimension. And what is the person doing here is to interact with a game that also includes haptic rendering information. So you can feel the stiffness of the rubber band that you are interacting with. Yeah, so that was my talk. And as a conclusion, so what we saw in the literature in our own experience is that the training effectiveness of different haptic strategies depends on the skill level of the person and also the characteristics of the task to be trained. And we have seen that in order to promote or enhance learning, we actually need to promote movement variability. That by providing, for example, random forces. And finally, if we want to enhance motor learning and more importantly, transfer of what is learned in the clinic into the activities of daily living, it's important to also include haptic rendering in order to enhance motor learning and recovery. And with that, I thank all my team and also the sponsors, and I will be very happy to answer your questions.
Thank you, Laura, for that interesting talk. Are there any questions? No questions. So this research, you've done all the research with upper body, right? You haven't done research with lower limbs.
No, I do both. Actually, the one with a stepper, the one in the MRI, it was with a lower extremity robotic device. So it was an exoskeleton for the lower extremity. But we also use it for the Locomat. We ran an experiment in Locomat where we were comparing also visual error amplification and haptic error amplification. And
the results are similar in sense of the outcomes, like what is important for learning.
Yes. So what we saw in the Locomat experiment, where we were comparing the visual error amplification and the haptic error amplification, because you may think that the benefit of amplifying errors is because you can detect those errors better, right? And then how can you detect this? I mean, if you do visual error amplification, you could also detect these errors better, right? And what we saw is that actually, even if haptic error amplification and visual error amplification were making errors more obvious to be detected, it was only the haptic error amplification, the one that was supporting the learning. And not only the learning of the task that was trained, but also the transfer to walking asymmetrically after the training.
Okay, thank you. Danny, did you want, I see you raised hand.
Yep, thanks, Tomislav. Thanks, Laura. That was really interesting. You have sort of partially answered my question actually in the previous answer, but I was wondering, you know, when you're talking about the difference between assisters need the haptic guidance and error augmentation, and not knowing which strategy would work better, and you have a sort of a blanket noise perturbation across. I was wondering if there's any way of selecting a more rich perturbation that has richer information, you know, the one that excites more information, useful information in learning the task. And is that perhaps what the somatic feedback is serving at the end, towards the later part of your talk? Is that because it has more information, richer in information content?
So the thing that it's providing, so when we are adding the noise, what we are doing is try to enforce the exploration of the environment, right? So you are forcing people to move through the local minimum that they reach, right? So it's similar to machine learning or reinforced learning.
Extreme seeking.
So you are enforcing them to explore more the environment, and I agree that it will be good to somehow guide them, you know, to certain areas of this exploration that you will be gaining more information. We haven't done this yet, but we are doing that. On the other side, the somatic feedback is different because it's actually providing more information. And more information is always better unless you are saturating the people and enhancing the cognitive flow too much. But you are doing it in a very naturalistic way, so this is not the case. This is also providing more information about the dynamics of the element you're interacting with, but I don't think that it's enforcing the exploration of the dynamics, right? So, I'm quite sure, because we have another study where we were comparing having this haptic rendering, and on top of that we have 3 different assistive controllers: the typical PD controller, a method creative control, and no control at all, right? So free, and the benefits were from having the model predictive controller, because the model predictive controller was allowing for more freedom to follow different trajectories, while the PD controller was reducing this exploration, right? So, and then you could see the benefits that it's the exploration, that it's independent on is independent of the haptic rendering of the pendulum dynamics. I hope I answered your question.
Yeah, no, certainly, yeah. Thank you.
Okay, so let's then move to the final part. Let's just thank Laura for her talk.
One last question, Heike had.
Okay.
Also some other time if there's no more time.
Well, if it's a quick one, it's fine. We are.
Oh yeah, quick question. So you're using these sophisticated exoskeletons like the Ironman, which have a lot of torque and power installed, and then you use much more clever algorithms like noise and or augmentation. I'm wondering, in terms of torques that you need for those, have you checked whether you could downsize the systems substantially to just render what you found is necessary to enhance learning? So could those motors become an order of magnitude smaller, for example?
Yeah, so that's a good question. That's something that I want to do for the lower extremities, but for the upper extremities, what I want is to have, so I want to use the devices that are already in the market and then provide more possibilities, right? So if you have somebody who is very disabled from the beginning, there is no point of having a amplification, right? And then you want to use the power of those motors. Well, if you have somebody, you know, that it's halfway the journey, then you can add things on top of it, right? So I agree that if you're in a clinic and you are always treating people who has less severity, then it's fine. You can diversify and have different devices. But if you could have a device that is already there and it's well accepted, and you can just enlarge the possibilities of using the device with a larger number of people, then for me, it's the way to go. But yeah, I agree that so if I will be developing new arm exoskeletons, then I will think about downsizing those robots, and then yes, keep the other ones that are already there for the more disabled people.
Thanks.
Okay, thank you. Let's then thank Laura for her talk.